So now we can introduce, of course, we solved it with zero inputs. That's not the most interesting thing. Sometimes interesting, of course, you will start with a sort of zero input circuit with initial charge still in place. But we would like to put some input to the circuit. So now I'll say Vs is some constant with time. Okay. Now the differential equation, as we already saw, was okay, which also could be written as sometimes it's written like this. For us, it's not very important because we're dealing with very simple cases. But many times the differential equation is written in this normalized form where the coefficient of the highest derivative is 1. Okay. So what's the solution to this one? How would you solve for this? There are many ways to do this. Okay. In fact, because it's a first order differential equation, you can even kind of integrate it. You get that logarithm and then do that. But I'll show a slightly different way, which is the reason to do this is that we know how to solve it for the case where the right hand side is 0. So we go on reducing everything to that case. Okay. And Vs is a constant. So if I call Vc1 as Vc minus Vs, the derivative here is the same as that, obviously, right? Okay. So what's the solution to this? This we have already found. What is Vc1? Some constant times exponential minus t by Rc. Okay. So this is just a change of variable to make the right hand side 0 and get a homogeneous differential equation again. And that tells you that for this Vc1, this is the solution. So what's the solution for Vc? It's Vs plus this Vc10 exponential minus t by Rc. Okay, and then Vc10 has to be again found from initial conditions. Okay. So I'll just call this Vc some V0 exponential, or maybe let me not change it, Vc10 exponential minus t by Rc. Okay. And let's say the initial value on the capacitor was some Vc0, okay, or maybe Vc of 0. So what is the value of Vc10? So Vc of maybe I think this will again, if I substitute t equal to 0, Vc of 0 should be Vs plus Vc10. So Vc of 0 minus Vs is this constant, Vs plus Vc10 at t equal to 0. So obviously Vc10 is Vc of 0 minus Vs. Okay. So this Vc of t can be written as Vs plus Vc of 0 minus Vs exponential minus T by Rc. Okay. Now, probably the case that you are most familiar with is when the capacitor starts from a discharge state, when Vc of 0 is equal to 0. What's the solution to that? So, Vc of t will be Vs minus Vs exponential minus T by Rc, which is okay. So, I think this you would have seen where in some the same, I think RL or RC circuits you would have seen this solution. But in general, if you start from a different initial condition, you will get this other solution. Okay, and it also makes sense because if Vc of 0 equals Vs, there should be no movement in the circuit, right? That is, this is equal to Vs, and then the current is 0, and there is no change at all. And that's what this thing says, right? This exponential completely goes away, and it says that Vc of t equals Vs forever. Okay, so these are all sanity checks that you have to also do, right? So in general, when you solve for something complicated, you should have different ways of solving it. While looking at the circuit, you should be able to tell some simple things about the solution. So in this case, I know that if Vc happens to be equal to Vs at t equal to 0, then there should be no change at all in the capacitor voltage. Okay. Now, does this solution make sense? If the capacitor were initially discharged, what is the current through the capacitor? If the capacitor is initially 0, what is the current through the capacitor? Vs by R, because all of this voltage Vs drops across the resistor. So, this current has to be equal to Vs by R, and it's that current that charges the capacitor, right? That is the current that is providing charge to the capacitor so that its voltage builds up. Okay. So, what's the rate of increase of the capacitor voltage? It's the current divided by the capacitor. If you have a certain current through a capacitor, current by capacitor is the rate of change of voltage. Okay. Current is the rate of change of charge, right? And charge by capacitance is the voltage. So, current by capacitance is the rate of change of voltage. So, initially it has to increase at a slope of Vs by Rc. Okay. If you differentiate it, do you get that? At the initial instant, you do get that, right? So, you get plus Vs by Rc. So, that sanity check is also satisfied. But as the capacitor voltage increases, what happens to the current? It decreases. Okay. So, the current, because this voltage is ramping up, the current will reduce. So, that means that the rate of increase of voltage falls. Okay. It doesn't do it in a piecewise manner like this, it does it continuously, but I am showing it that way. Okay. And it falls further and further and further until it just starts slowly creeping up to the final value. What's the final value? Vs. Okay. When this final value, when the voltage across the capacitor is Vs, the current here becomes 0 and voltages and currents in the circuit stop changing. Okay. So, and that is known as steady state for this circuit with a DC input. Okay. That is Vs. For DC inputs, in steady state, there is no current through the capacitor. Okay. So, this one asymptotically reaches Vs. Okay. But this business of finding out what the initial slope is, etc., you should be able to do even without the solution, right? Just by looking at the circuit. By computing the currents in the circuit, you can tell how much current is going through the capacitor. That tells you how fast it is changing, how fast its voltage is changing. Okay. So, what this result says is that for this circuit, if you have Vs to be a constant, R and C with an initial voltage of Vc of 0, the solution was Vs plus Vc of 0 minus Vs exponential minus t by RC. Okay. So if you plot Vc of t, and let's say Vs is somewhere here, this is the value of Vs. Now if you start from 0, it will do that. It will never reach it, but only does it asymptotically. And if you start from some middle value, let's say, let me put numbers here. So let me call this 5 volts. So the initial slope here is 5 volts by RC. And let's say it starts from 3 volts. Okay. What happens then? What happens in that case? It will still go to 5 volts. But what will be the initial slope? Will it be the same? It will be. That's most obvious by looking at the circuit, because you have 2 volts across the resistor. So 2 by R is the current, and that by RC is the 2 by RC is the rate of change of voltage. So it starts with a smaller slope, but it will asymptotically reach the same value. And you can also start from a higher voltage, let's say 8 volts or something. Then again the same thing happens, except that now the current is backwards, because the capacitor voltage is larger than this voltage. The current goes that way, it discharges the capacitor, and it discharges to the same 5 volts. Okay, and the time constant is the same in all cases, it is RC. Okay, now if you start from 0 volts, okay, if you take this case which I have shown here, what is the value reached at t equal to RC? What's the value of the capacitor voltage? So it will be Vs times 1 minus 1 by E, where this is the natural exponent, and this is, how much is this? 0.636, I think. Okay, I'll remove the last decimal because I'm not sure. So it will reach somewhere here. Okay, and in fact it's more obvious from the other case, where in this case what happens in one time constant? What will be this value? 5 by E, 5 by the natural exponent, which is about 37% of the initial value. Okay, so basically it changes by about 63% in one time constant. Okay, and that is true of wherever it starts and wherever it finishes. Okay, if you define this as 100%, in one time constant it would have gone 63% of that. Okay, so these are all some useful things to remember. I mean, not necessarily memorize, but understand and remember. Okay, and what will the currents look like in each of these cases? The currents through the capacitor, when it starts from 0, what is the initial current? 5 volt by R, and current goes to 0. Okay, and similarly when it starts from 3 volts, what is the initial current? 2 volts by R, and that also goes to 0. And when it starts from 8 volts, it is minus 3 volts by R, and that also goes to 0, and with the same time constant, of course. Okay, so the currents through capacitors eventually become 0 with constant inputs. Okay.